So why do we get that splitting of the orbitals in an octahedral geometry? Happens in other geometries. We're focusing right now on octahedral. Well, there's several theories have been advanced to explain this. One of those is hybridization, and I would spend a slide on hybridization if you were in my first year university class, but we haven't really talked about hybridization, and besides which it's a bogus for coordination compounds, so we'll skip it and we'll move straight into what is called crystal field theory. Okay, now let's start from scratch. Here are our orbitals in a bare metal atom. Right, metal atom's got the 5 degenerate d orbitals. Here's an energy level diagram I'm drawing. So they all have the same energy. Okay, now in crystal field theory, what we do is we say pretend that around that atom there's a spherical electrostatic field that is repelling the electrons on the atom. So of course that will, if it's a spherical electrical field, which we call the barycenter, nothing special about that, just means the middle of a big thingy. Okay, so we raise the energy. So there are the energies of, in our imaginary spherical electrical field, the d orbitals. So to raise a little bit of energy because of the repulsion. Then we think of the ligands as being point charges. So the ligands are point charges, they're electrostatic point charges, okay? And the closer that the orbitals are, the electrons in the orbitals, or the orbitals are on the metal atom to pointing at the ligands, the more destabilized those orbitals become because of that repulsion. So you've already destabilized the d orbitals en masse with this spherical electrical field, and now we're replacing, or within that spherical electrical field, we put the ligands that are particular point charges. Okay, now imagine then in our octahedral electral field, okay, we've got ligands along each of these axes. We've got ligands on the x, the y, the z, the minus x, the minus y, and the minus z positions. Okay, well, we've got 3 orbitals that are not pointing directly at those ligands, and then we got 2 orbitals, the dz squared and the dx squared minus y squared, that are pointing exactly at those ligands. Got a ligand here, pointing there, ligand there, pointing there, ligands here, 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 all pointing directly at the dx squared minus y squared, or the dx squared minus y squared, are pointing at those ligands. So these get destabilized even more, but these get destabilized or stabilized, excuse me, because they're pointing in between the ligands. So that's the splitting explained by the crystal field theory, that the ligands are little repulsive point charges, and the closer that the orbitals are to pointing at the ligands, the worse it is for those orbitals. So our 3 groups there, dxy, dyz, and the dxz, the ones that are pointing in between the axes, and the dz squared and the dx squared minus y squared, the ones that are pointing straight at those ligands. Okay, octahedral field splits into 2 because 2 of the orbitals are pointing directly at the ligands, so those are the higher energy ones. 3 of the orbitals are pointing in between the ligands, those are the lower energy ones. Now a little bit of notation here. That energy split is called the crystal field splitting energy. Okay, the splitting energy, the energy of the split, as described by our crystal field. Our crystal field is those point charge ligands. In an octahedral compound, we call that delta oct. So delta, of course, difference between the energy levels, oct because it's octahedral. And these split in a predictable fashion. The 2 destabilized ones go up by 0.6 of that split. The 3 stabilized ones go down by 0.4 of that split. Now, you're not going to worry too much about 0.4 and 0.6 right now. There is an extension video going into more detail about crystal field splitting energy, or CFSE for short. Okay, so here we've got a crystal field theory explanation, and that is that the ligands are actually giving rise to this separation. The closer an orbital is to pointing directly at a ligand, the worse it is for that orbital. The more that they're pointing not at the ligands, so right in between the ligands in this case, the better it is. Full stabilization, the full splitting, delta oct. 2 of them go up by 0.6 delta oct, 3 of them go down by 0.4 delta oct. So notice, by the way, the total energy cancels out because 3 times minus 0.4 is equal to 2 times plus 0.6. We label these just for convenience for now, although these labels have a very important significance as you get more into symmetry considerations and chemical group theory. But the lower group are called T, 2G, and the upper group are labeled EG. And I will use those throughout just to make it easier to refer to the stabilized group of 3, T2G, and the destabilized group of 2 orbitals, EG. So let's continue to discuss the crystal field splitting energy. Remember the crystal field splitting energy, delta oct is the gap between the stabilized and the destabilized group. And remember that they are split because of the ligands forcing them apart. Now, delta oct obviously therefore depends upon what the ligands are. Delta oct can be really large. Right, when you have what's called a strong ligand field. And of course, remember, if delta oct is large, that means we have low spin. Delta oct, on the other hand, will be small when you have a weak ligand field. And when, of course, you have a weak ligand field, delta oct is small, not a big gap here. That's when you get the high spin considerations. Okay, so whether you get low or high spin depends on several factors, number one of which is what are the ligands. There are some ligands that really repel those orbitals, so they have a massive stabilization and a massive destabilization, and so a really big splitting here. Those are the strong field ligands. And then you have ones where they hardly have any splitting at all, the really weak field ligands. So very small delta oct, small splitting, small delta oct means high spin. Okay, well, there is a series called the Spectrochemical Series that lists these ligands here, where we start off with carbonyl and cyanide with a very large delta oct, and then we go down to the halides with a very small delta oct. Now, if you look at this, you can tell there's a certain little pattern to this. Our large delta oct carbon ligands, and also if I put the phosphines in here, where phosphorus is the binding, the coordinating atom, that would go here. So carbon and phosphorus, and then you have the nitrogens, right? Fen, bipi, N, ammonia, pyridine. There's the nitrogen end of thiocyanate. Then you get the oxygens. So here's oxalate. There's the oxygens for water. There's hydroxide. Then you have the halides going fluoride, and then chloride, bromide, iodide. Here's one of those pseudo halides, azide, that while it's a nitrogen, so should be up here, it's actually stuck down here between fluoride and chloride. The sulfur end of thiocyanate right here. Okay, so essentially you get it's much more than electronegativity. Obviously you have the non-electronegative ones up here, carbon and phosphorus, then nitrogen, then oxygen, and then fluoride. But then you go back down again, electronegativity. Fluoride is a stronger ligand than chloride, which is stronger than bromide, which is stronger than iodide. There are good explanations for this series when you move from so-called crystal field theory to ligand field theory, but I'm certainly not going to touch on that in this particular course. Now, if we look at a series of complexes, we can actually get a feel for this spectrochemical series when we look at the size of delta oct, and you can measure delta oct using spectroscopy, and we'll touch on that in the next couple of slides. But anyway, the units of delta oct that are favored from spectroscopy, centimeters to the -1. Centimeters to the -1 is ultimately proportional to the energy. Okay, so the higher the value of delta oct, the higher the value given here, the bigger this splitting. So if we look at some chromium-3 complexes, we have cyanide. Cyanide is a very strong field ligand, so a large delta oct. There's the large delta oct. Then we have ammonia, then water, where here's ammonia, then water. Ammonia is a stronger field ligand than water, and we can see that with the size of delta oct. Okay, 21,600 down to 17,400. And then after water, we have fluoride. Fluoride going down there into the weaker field ligands, and you can see the smaller delta oct. We can see the same series for some ion complexes. They're cyanide, oxalato, water, cyanide, oxalato, water. Notice oxalato and water I've put in about equal, and look at that, pretty close to being equal. Certainly 400 is nothing when you look at the gap up, 21,000 between the oxalate and the cyanate. And here's some cobalt species. So we have ethylene diamine here, stronger than ammonia, stronger than water, stronger than fluoride. You can add in some extra little patterns into this if you know your ligands nicely. If we look at the nitrogen list here, Fen is bidentate, BiPi is bidentate, N is bidentate, ammonia is bidentate, pyridine bidentate. All of these are bidentate, all of these are neutral. So you have the bidentate, then the monodentate, and then you have the anionic. See the same for the oxygen ones. Oxalate here, bidentate, neutral, and then monodentate, anionic. Oxalate, of course, is bidentate but anionic, so you actually see that that makes it about equal to the neutral. And then, of course, down here we have the anionic ones. Some other factors other than ligands are, of course, the metal. Well, the higher the oxidation number of the metal, then the larger the delta oct. And also the third row has got larger delta octs than equivalent complexes from the second transition metal row, which are greater than those for the first transition metal row. So if we look here for that, platinum 4 and iridium 3 have got much higher delta octs in their complexes than these second row ones. Palladium, rhodium, molybdenum, and ruthenium, and those are higher than some selected first row ones, cobalt, chromium, and iron. Notice that there's not a nice little sequence. If we go chromium bigger than cobalt, bigger than chromium, bigger than iron, there's cobalt, there's chromium, there's iron. So while we can say that first row is smaller than second row smaller than third row, we can't really have a sequence within the row. There are just too many other factors associated with with values of delta oct, with what might lead to different values of delta oct. But some nice generalizations there. Ligands, you've got the spectrochemical series, and then for metals, the higher the oxidation number, the bigger the splitting, and then third row more than second row, more than first row. We can apply the same idea of the splitting to other geometries. I do a little bit of this in one of the extension videos, but at A level you do also talk about tetrahedral to an extent, so it behooves me to mention that a little bit here. So there's our octahedral splitting, with which you are familiar. There are the d orbitals depicted from which that splitting occurs. If instead of having an octahedral field, we put them in a tetrahedral field, well, here's a tetrahedron, okay? And the first thing I want you to notice is that no way, right, are these ligands here that are on the corners of boxes having the axial orbitals pointing at them. So in other words, the dz squared pointing this way, it's not pointing at those ligands, nor is the x, nor is the y-axis, okay? So far from these orbitals that are along the axes being destabilized, they're actually stabilized. Now, these ligands and the corners of the boxes, if I was to be able to draw in, which I'm afraid my artistic skills escaped me, okay, none of our in between the axes ligands orbitals are actually pointing at the ligands. If you look here, this would be where the XZ is. It's not pointing at this ligand, but it's kind of close to it, okay? And in the same way here, if we think about this is the XY pointing here, it's not pointing at this ligand, but it's close to it. So what we see is that in the exact opposite way for the octahedral, that the orbitals along the axes are stabilized, the orbitals in between the axes are destabilized. Again, nomenclature of it, the pair are called E, not EG, we lose the G, but E, and the three are called T2, not T2G, again we lose the E. Now, what you should notice here is that the splitting, right, the so-called delta tet, is much smaller than the splitting for delta oct. Indeed, delta tet is 4/9 delta oct for a particular metal or a particular ligand. And that comes from two particular reasons. The first reason is that, of course, delta oct, this splitting, is due to having 6 ligands. Delta tet, you've only got 4 ligands doing the splitting. So therefore, you should expect 4 ligands to have a much smaller effect than 6 ligands. But the other difference is that there is a much bigger gap between the orbital behavior on the ligands. The EG in octahedral are pointing right at the ligands. None of the orbitals in the tetrahedral geometry are pointing right at the ligands. We can say that the axial ligands, the ones along, or the orbitals along the axis, are further away from pointing at ligands than the diagonal orbitals are to pointing at the ligands, but neither of them are pointing directly at the ligands. Thus, the ligands have a smaller effect. So fewer ligands having less of an effect, delta tet is smaller than delta oct. Okay, and the values in particular are the same, but again switched. So we got 2 orbitals stabilized by 0.6, 3 orbitals destabilized by 0.4. Octahedral splitting, tetrahedral splitting. And in one of the, again, the extension videos, I actually compare some of the energies associated with octahedral and tetrahedral and use it as an argument as to why one observes tetrahedral geometries in some cases and not in others. Now, tetrahedral complexes are usually high spin, and I'm going to ask you to think about that yourself. Why will tetrahedral usually be high spin? In other words, if we were to start putting in electrons, we'd go 1, 2, 3, 4, 5 instead of 1, 2, 3, 4, 5. So tetrahedral, high spin. Octahedral, you can have low spin, you can have high spin. It depends upon the ligand, it depends upon the metal, it depends upon the oxidation state of the metal.